All right, good morning. Welcome back. Okay, so you're gonna notice first things first, right off the bat, this looks weird. This is not your comfortable, normal, whatever. I'm in a different spot. Okay, it's a thing that happens infrequently these days, but we're gonna go with it. Um, yeah. This handful of days is strange, and I'm not gonna go too deep, but that's just what it is. Okay, I also just moved my paper. Okay, so things that we're doing today, we are along in the theme of things being weird, right? Okay. I could make finger puppets. This is not what this video is about. Okay. Okay, so in the theme of things being weird, what we would typically expect is that on a Thursday you would get a review guide, and on a Friday you would get a quiz. But as we've mentioned, things are weird. And so what we're gonna do instead, despite the initial revision yesterday, okay, so we're gonna look more at Electron configurations today. And we're gonna clear up a few just kind of little things. I looked through your work from yesterday, and I think we're getting some meta level questions, so I want to address some of those questions, and just do another recap on like how to do this kind of stuff. I'll also post the answer video like usual. Some of you are totally crushing it. Like, you got it, you got the ideas, you're getting where you're going, it's fine. I will just acknowledge that some of you are finding answers on the internet and writing them down, and that's not fine. And but what it looks like to me when I see stuff like that is that maybe you don't know how to do it, or like feel like it's really confusing, you're not really sure. So that's kind of what the purpose is here, is to get us all entirely sure and confident, and like there'd be many things like this, but it's kind of like riding your bike, you know, like once you get the hang of it, it's really not so bad at all. That being said, some of the tools that are really helpful for students we can't do because we're virtual, so that stinks. There's an entire like set of stuff that I do every year that I can't do because you already folded a periodic table. You're not gonna, like, no one is asking for any more than that because that was already a lot in that realm. Okay, so today we're gonna do another little thing on electron configurations. I previewed you the full configurations are kind of like Bohr structures, so and that the core notation is kind of like a Lewis structure, and then I didn't actually show you how to do that at all. So today, recap on electron configurations, introduce core notation, and then we're actually going to merge this week and next week in terms of like review and quiz and stuff like that. So and Tuesday, about a third of everybody is taking the ACT, so Tuesday is going to be a really light day, by the way. Yay! I'll send you a bunch of stuff on Monday, and it'll be due on the end of Tuesday. So you just have 2 days to do, and you'll watch each other's projects Monday and Tuesday, and take some notes about groups, and that's that. Wednesday, I'll teach you an entire new bucket of things, and then Thursday next week, we'll do a review guide and a quiz, and it'll kind of be like 2 weeks in one. And okay. All right. The other exciting... Okay, so that's like your overview. I could write that, but you can also read mine. Okay, so today we're going to do electron configuration and core notation, getting you kind of the Lewis structure of electron configuration. Monday and Tuesday, you'll watch each other's videos on groups. On Wednesday, I'll get you another bucket of stuff, and then Thursday and Friday we'll have a quiz on orbitals, size and shape, electron jumps, electron configurations and core notation, groups, and trends. Cool. Yeah, there's somebody, I did a one-on-one yesterday, and somebody was like, when are you gonna mention the photons? You might know from like somewhere else in your world that if we're talking about light, right, like all these electron jumps that we did on Monday with the colors of the flames, those are all photons. Anything that you can see is a photon. So electrons release photons when they leap between energy levels, which is wild. How does that happen? Why? What is a photon? Okay, this is why I didn't mention it, because photons are part of this particle wave duality system that I go into in physics and somewhat less in chem, especially virtually. But if you're into wave particle duality, either let me know or take physics. Both are very valid options. Because I love stuff like that. Okay. All right. So today, let's do today. I've realized with my unusual setup that this is an unusual opportunity to show you more than the normal amount of stuff on screen. So you're well aware that usually I can barely show you a single page. But without going into too much detail, this gives me a way to do this. And I actually can duplicate it in my other environment as well. Okay, so here's the whole thing. Don't worry, we will add color. When you do your groups, you're gonna color all of this in a beautiful rainbow of color. Okay, but for today, we're doing electron configurations and core notation. Okay, and let's just jump in. Okay, I think a lot of people are making sense of the S block stuff and the P block stuff. Got some emailed questions, got some, like, I can see your kind of confusion around D block stuff and F block stuff. So to get us warmed up, let's do one S and one P, and then get into this D and the F. Now, if for whatever reason you're like, this doesn't make sense, I'm looking up online, and today you're like, wait a second now, the great all-knowing internet told me one thing, and my teacher is telling me something different, and that's confusing. That may be the case. As with many things, we are learning the language here, and then if you go into research chemistry, they will tell you why it is not always that way. But they're looking at the wavelengths, and they're looking at the magnetism. I think we very briefly discussed magnetism to figure out the actual configuration. This is kind of what we would expect, and sometimes research tells us that, like, sometimes elements actually do other things. So your internet is going to tell you what the research shows elements actually do. What we're learning in year 1 chem is what we predict they should do, because it's that prediction that we use to, like, do the research. Okay, and in this case it's the predicted version that we're actually looking for. Okay. Cool. Let's just jump in. So you've done a few of these by now. So I'm going to go a little bit faster overall. And, okay, but our goals here, we're going to do an example S. These are electron configurations. Electron. Here's kind of our, now this is an issue. With the zoomed out system, you can't see my, didn't prep for that. Okay. Alright, so we're going to do an example S and P to kind of get ourselves warmed up, and just to see another, like, how do I write electron configurations. Then we'll get into D's and F's, and then core notation. Actually, I'll do core notation right along. So we'll do core notation for these also. And that's nice because you'll actually see, like, why it's so amazing. Okay. Randomly choosing an S block element. Let's do from the S block And again, S block just means that these have the simple shape of a sphere. Anything in the S block, when it goes to react, it will more or less act as if it is a sphere because that is its dominant shape. Let's just do calcium. It's got 20 protons, 20 electrons. That's just a reminder of what we're looking at. Okay, here's where the zoomed out camera thing is going to help us, hopefully, maybe. Because what we're looking at is the whole thing. Alright, so we're going to calcium, which is here. And we start at the top left corner. We work our way across every single time. So every time we'll start at hydrogen. Here's hydrogen. Calcium's bigger than hydrogen, so we're going to fill our 1s, hydrogen and helium. So there's going to be 2 electrons in our 1s, hydrogen and helium. This may not actually be better at all. Okay. 1s is filled with 2 electrons. Forget the zoom. We're going to do this like normal. Okay. So calcium 1s is filled with 2 electrons. You've got your 2s. 2 elements there, lithium and beryllium. That 2s is filled with 2 electrons as well. 2s is filled with 2 electrons. After that, skip across all your blank space here. Go into your 2p's. 2p's. 1, 2, 3, 4, 5, 6. Decent chance you've got this already. I shouldn't give too much on this. Calcium's bigger than the 2p, so it's filled with, the 2p is filled with 6 electrons. Back to your s block. Now we're under the 3rd row. So we've got 3s. Calcium's bigger than your 3s. That's filled with 2 electrons also. Over to your 3p. Calcium's bigger than a 3p, so the 3p is filled with 1, 2, 3, 4, 5, 6 electrons. Alright, so our 3p is filled with 6 electrons. Over to your 4s. Calcium is here. So we're looking at the 4s block, and we've got 2 electrons. Calcium's got a 4s too. Okay. Alright, okay. Oh, let's do some core notation. Alright, to do core notation, you're going to look for the noble gas inside this atom. If you're like, what's a noble gas? Okay, let's write that down and then we'll figure out what is a noble gas. So we're going to look for the noble gas inside. It's the core notation, right? So we're looking for the noble gas inside this atom. Okay, which brings up the great question of what is a noble gas? And this is gonna, a lot of y'all did projects on noble gases, and you'll watch each other's group presentations Monday and Tuesday. But for now, things to know about the noble gases. They are super stable. So with this core notation stuff, your noble gas is so stable that it's probably not going to break. So once we find the noble gas inside, we can put it into this core form, because the noble gas core is not gonna break through any natural, I mean, like, these are hard words because, like, supernovas are also natural, so, like, and supernovas can do some pretty bonkers things, but, like, on the surface of Earth, with the type of heat that we typically have here on Earth, like, we're not in a star, we're living on a planet on the surface, so, like, with, like, you have to do some really bonkers stuff to break a core. We can do it, but this is high school level chem. That is super graduate level chem. Okay. Great. So noble gases are really stable. Really stable. and they are located over here. So you've done your whole giant table, and you've learned to either love or hate it, as the case may be. And this is not super great, but it's good enough as an outline of the whole table. And your noble gases are over here. So we will color in your giant table Monday and Tuesday. But for now, these are the noble gases. Okay. We can even, on the wall at Pym, these are purple. Because they're like super stable. That purple didn't show up anyways, so like never mind. Okay. Great. Oh, the other key here is we're looking for the noble gas inside the atom. So this is not the closest noble gas necessarily. It may be, but it may not be. When you're on the airplane, you look for your nearest exit, whenever that day will be again. But for your noble gases, you're looking for the noble gas inside your atom. So there's two ways to do this. You can either look from your full notation, look for your biggest full p orbital. So that would mean look for your biggest full p orbital means like take this electron configuration, find the biggest p that has 6 electrons in it. So here we have 2 p orbitals, we have a 2p filled with 6, and we have a 3p filled with 6. If you had a 4p filled with 6 or a 5p filled with 6, whatever, find your biggest full p. That is your core. Because your noble gases are over here in the p block, and they're that 6th row in your p block. So your noble gases are your full p orbital at that point. So whatever the biggest p orbital that you have filled with all 6 electrons, that's your noble gas inside. Okay, so in this case our biggest full p is the 3p filled with 6 electrons. So look for your biggest full p and then find it on your table. So we've got our 3p filled with 6 is what we're looking for. So in your p orbitals, look for the noble gas on the 3rd row, and in this case that's argon. I'm just going to write that in. My idea here is that I don't want you to have to write in the entire periodic table, because that just seems like a lot to do when you're already doing a lot. So we'll fill in the things that we need to have. We could just fill in, let's take a hot second and fill in. So we've got helium, we've got neon, we've got argon. I'm just going to make sure that I don't mess up these bottom few. 36 is krypton. Yeah, it's actually krypton. 54 is xenon. It's cool if you've never heard of that, that's totally fine. Number 86 is radon. And number 118 is not anybody's core, because this is the biggest element we know of, but I guess it is its own. Organocin. I don't know who named that or when they did, but some of your periodic tables don't even list that because they were printed before it was synthesized, discovered, made. I mean, none of this stuff is natural per se. This is largely somebody in Chicago who's really into putting more protons onto elements. I mean, Bohr spent his whole life looking at hydrogen. There are folks across the world, but there's a big lab in Chicago who are spending their lives looking at stuff like organocin. Good. Okay. Now, most of us exist in the realm of life, which is up here in this region. Okay, so we figured out the noble gases and what they're called. Okay, and it's those noble gases that will be the core of your other elements. Okay, so back up to here. Calcium, We found the biggest full P. We found that it's the full P in the third row that is the core of calcium. Find the full P in the third row. That's argon. Okay. And you can even check it, because argon has 18 protons and electrons. Calcium has 20. So argon is inside of calcium. We're looking good. That's what we want. We want the noble gas inside the atom. So we can either look for the biggest full P orbital and then find that element. So what I mean by that is here we we found our biggest full P is a 3p with 6 electrons in it. We look for the biggest full P. We found it 3. Find that element. So we found that our full 3p was argon. So when we write our core notation, the core notation for calcium again, that's just 20. I don't know why I'm adding that today. It's not super relevant. 20 protons, 20 electrons. When we write the core notation, we'll say this core is argon. And we can just put that argon in a little brackety box. Who knows why? Goes in a little box. And then on the outside, write everything after. So in this case, calcium's in the S block. We've just got some S stuff after. If there's a whole bunch, find the noble gas inside. And when you write the core notation, put that noble gas in brackets and put everything else after. So noble gas in brackets and everything else after. Okay, and everything else after is just like anything else. There we go. Okay, can't see all of it. That's good. So the noble gas goes in brackets. Anything else after that goes after. Okay. The other way to find the noble gas inside is to backwards typewriter your periodic table. So if we're looking at calcium, here's calcium, and we just take ourselves backwards and up instead of forwards and down. So typewriter is gonna like get to the end of a row and ding, back down to the beginning. Backwards typewriter just it's a joke. You go back to the beginning and then up. Okay, so calcium would take us back to the beginning of 4s, and we would go up to the end of the 3p. That's the other way to do it. They'll get you to the same spot. I just wanted to show you both. So either just find the noble gas inside, kind of using the manual method, or find the biggest full P that you've got in your electron configuration and go that way. Okay. Let's do a P with a little bit less stuff in it. Let's do fluorine. Okay. So fluorine is, we said we'd do an S and a P, and then core notation, and then the bigger things, right? I still have to show you those. Okay, so fluorine has 9 protons, 9 electrons. Fluorine's over here. It's in the P block. This makes sense. This example is from the P block. I could maybe, if you're getting the hang of it, I can show you on this one. There's fluorine. Start at the top like always. Here's your hydrogen, helium is your 1s. There's 2 elements in your 1s, just like 2 electrons on your inner bore. So we've got a 1s2. Loop around to your 2s. 1, 2, because fluorine is bigger than beryllium, so we've got a 2s filled with 2 electrons. Over to your 2p. Fluorine is here. So your 2p has 1, 2, 3, 4, 5. It's not quite full. It's not full with all 6. That would be neon. We're just looking at fluorine. Okay, so fluorine, you might start to notice that fluorine has 1 less than it wants. here's a clue to all your group stuff next week. Elements that have something they want tend to go get it. So fluorine having only 5 in its p orbital is unstable, because it's like so close to neon. It can like see this thing it wants to be full, it wants to be that stable, full inner core element thing, and it's so close, and yet it's not there, and so it can do some pretty wild things to get there. And by wild things, I mean fluorine will destroy anything else. Hopefully your halogen folks have talked about some of the things halogens can do. Preview, halogens are next to all the elements of life over here, and since the halogens are closer to the noble gases, strong, stable, I want to say confident, but that's just personification like nuts. Yeah, like these strong noble gases, fluorine's so close, it really wants to get there. It's even closer than oxygen. Fluorine can rip up and destroy life. That's what makes it cool. Chlorine can also rip up and destroy life. So can bromine. Your halogens are toxic because they're stronger, because they're almost noble gases, but they're not quite there yet. Okay. So we wrote an electron configuration for fluorine. We saw that fluorine is so close to that noble gas core of neon, but it's not there yet. It's only at 5 electrons, not 6 in its p orbital. Okay, let's write some core notation for this. Core. We're going to look for the noble gas inside the element. I told you earlier, look for the biggest full P. Really, it's the noble gas, right? So if we're mostly looking at the biggest full P, is there any other element in the noble gas column, even though it doesn't have a p orbital? You're looking for helium. Helium is your core of fluorine. That's the noble gas inside of fluorine. Even though it is 1s2, there's no p. It breaks this rule. Oh dear. Okay, so this should say look for your biggest full p orbital, or if you're on, if helium is the noble gas inside, go with helium. I hope that makes sense. Fluorine's here. There's no full P inside of fluorine. So we'll go to the 1s is the biggest full noble gas inside of fluorine. That 1s is the core. We can write it just as that element symbol, and then everything else goes outside. Okay, and now we can say it has a core of helium, and then 2s2 and 2p5. Okay, good. All right, let's get down to where core notation really shines, which is the big stuff. All right, so we're going to do a D element and an F element, and part of why we're doing this is just to show you how this works. I'm going to do all of this with my little table instead of my big table in hopes of being visually a little bit less wild. And you're kind of getting the hang of it, and you're kind of starting to see the blocks, the S block, the P block, and then the trickier blocks, the D block and the F block. Okay, so we're going to do a trickier one. We did nickel. Let's do molybdenum. I have a friend who researches molybdenum. She is spending her life trying to get the state of Wisconsin to let her build a nuclear reactor so that she can form radioactive molybdenum, which is useful in medical procedures. Currently, we import all of it, and it costs a lot of money, but if she could just do it in the US, then, in theory, medical costs might be a little bit lower. This is not just a blatant plug for my friend. It's also why molybdenum is cool. Can be used in medicine. And they affectionately call it Molly, by the way. Okay, but let's just go with it. We've got molybdenum, element 42. So we've got 42 protons and electrons we're keeping track of here. Just realized I can rotate my camera, but how about the other way? Okay. Whatever. Sorry, I should just go with it. Okay, so molybdenum is here. And we start from the top. Off we go. Molybdenum's bigger than 1s. We've got hydrogen and helium. This is like the inner circle of the Bohr. That is a 1s, and there's 2 elements in it, just like the inner circle of your Bohr has 2 electrons drawn on that first circle. Synergy is powerful. Okay, on the second row, we've got the 2s. Molybdenum's bigger than a 2s. It's full with 2 electrons. 2s2. Over to the 2p's. This is your p block on your second row. 1, 2, 3, 4, 5, 6. That's full with 6. Still going down to your 3s. 3s is filled with 2 electrons. 3s2. Over to your 3p. 1, 2, 3, 4, 5, 6. Your 3p is filled with 6 electrons. Keep going. Here's your 4s. 1, 2. Your 4s is filled with 2 electrons. Just when you start to get comfortable is when things go weird. Okay. Okay. So this was your 4s, 4th row s block. That made sense. Your d's are where things start to get bizarre. Your d's are one size smaller than you think. So we're on the 4th row. So this is a 3d. Molybdenum is bigger than a 3D, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got 3D10. Keep going, we're not there yet. Back to our P's though. P's are what we think they should be in terms of size. So 4th row P block, that is a 4P. And here we go, 1, 2, 3, 4, 5, 6. This is a full P orbital with 6 electrons. You may be thinking right now, okay, that's a noble gas, and it's the biggest noble gas inside of molybdenum, because once we get to know molybdenum, that's where we'll stop. So that actually is the biggest noble gas inside of molybdenum right there. Interesting. Okay. Back to this side, 5s2, that's full. And we're back in our D's. Our D's are one size smaller than you think, so that is a 4D. And we'll just start from, this is the beginning of the D block right here, the beginning of the transition metals. Yttrium is also very cool. 1, 2, 3, 4, and now we're at molybdenum. So it's got 44. If you were to look this up online, it would tell you something different. Can I do this in under 60 seconds? It would tell you the 5s had 1 and the 4D had 5, because what they found is that molybdenum is stable enough and magnetic enough that it's got 5 unpaired electrons in this 4D orbital. And with that, since we can see that, we predict that it's pulling 1 electron from the 5s. Things like to be stable. They like to be either full or half full. However, we're not going to go deep on that virtually. Sometimes we do in person, but virtually, let's just, this is what you would predict, given your knowledge of things. This is what we're going to go with here. If you're into weird electron configurations, let's do it, but I'm not going to make the whole class go there. Okay. So we're going to find your noble gas core. We can either do this the reverse typewriter method, where we start from molybdenum and we go doop, 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 ding, and we go up a line to find the noble gas inside that way. Krypton is what we're looking at. Or we can find our biggest full P, our P orbital is 6 electrons in it. We've got a full 2P, we've got a full 3P, we've got a full 4P. 4 is the biggest. That 4P, okay, so the noble gas on the 4th row is also krypton. They'll get you to the same place every time. Okay, so that's our noble gas core. That's the biggest full P inside. When we write this in core notation, we can put that krypton in a little box like that, and then everything else comes after. And there you go. Okay, so again, the core notation is nice because you can condense all this stuff into just writing the noble gas core. But it's good to know where it comes from, right? and to know like what to write after it. Okay, let's do another wild magnet, neodymium. Every once in a while, I have magnet nerds in class, which is fun because neodymium magnets, if you have like fridge magnets that like don't come off the fridge, that you have to like slide off the side because they're so like stuck to your refrigerator, that's probably a neodymium magnet. If you have a knife block, like a magnetic knife block on the wall, that is a neodymium magnet, hopefully, because it's trying to hold the knives off the ground. Neodymium is a very strong magnet. Okay, it also has 60 protons, 60 electrons, and it's in the F block, so we're gonna just do this. Okay, start from the top. Some of this will go a little bit faster. We've got a full 1s with 2 electrons. We've got a full 2s with 2 electrons. We've got a full 2p with 6 electrons. I'm doing this faster because neodymium's in the F block, which is like down below. Here's your 3s with 2 electrons. Here's your 3p with 6 electrons. Here's your 4s with 2 electrons. Here's your, oh, I can do that. Okay, here's your 3d with 10 electrons. Here's your 4p with 6 electrons. That went a little bit faster because, oh, and it's off screen. That's not fair. Okay. I did that faster in part because all of that is also inside molybdenum. We're going to keep going with neodymium, but that's why I did that a little bit faster. Okay, now it's on screen. That's always helpful. Let's keep at it. Here's your 5s. That's full. Here's your 4d, one size smaller d. Okay, so your 4d goes across to cadmium. Okay. We're looking for neodymium, which is 60. Cadmium's smaller, so it's got a full D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For full Ds have 10 electrons. We get up to our 5p. Back to the p block. That's the size we think it should be. Okay, full p ends at xenon. 54. We're looking for neodymium. 60. We're getting close. That's something to note. It's smaller than what we want, and it's a noble gas, and it's really close to what we want. That's cool. Okay, but this 5p is full, so on our thing, we're going to say 5p6, because that's a full 5p orbital. To your 6th row, here's your 6s. That's full also. That gets us to 56. We're getting close to 60. That 6s is filled with 2 electrons. Now we're down to your F. Your F is 2 sizes smaller than you think it should be. That's a 4F. Okay, here's where you're going. Neodymium. 1, 2, 3, 4. Alright, so in that 4F, 4 electrons. Same thing here. The internet's going to tell you something else. Or it might not. Your strong magnets probably have a little bit more than 4 unpaired. But this is what you would guess. This is where we're going to go. I'm going to let you get the really weird electron configurations later. Okay. So 2 days ago, that looked like a lot. And by today, you're kind of like, yeah, I'm getting the hang of it. Like, it's really not so bad. Like, it's a lot, but it's also, like, predictable at least, which is nice. Okay, so here's your neodymium. We're looking for the noble gas core inside. We can either typewrite it, reverse typewriter it backwards, row 6, boop, up to row 5, and the noble gas over here. Or we can find the biggest full p orbital inside the full notation. Okay, reverse typewriter gets us to xenon. Biggest full p, we've got a 2p6, a 3p6, a 4p6, and a 5p6. Okay, the 5p6 is the biggest of these. And our 5p6 is xenon. They'll both get you to exactly the same place. So all of this can be condensed into bracket xenon, and then everything else after. Okay. Great. Great. Okay. Let's leave this there. I'm thinking you're getting a stronger handle on electron configurations in general, core notation, so we'll do a little bit more practice with electron configurations and core notation. And good news, there's no heavy. It's not like Wednesday. I feel like Wednesday there was too much stuff. So it's not like that. It's just a few more practice to get the hang of it. On Monday, you'll watch each other's group videos, and Tuesday, actually. And then Wednesday, I'll teach you trends. And then we'll start building ions and then molecules. Okay, see you soon.